we'll go ahead and start recording. I'm just going to go ahead and pin my video here, or leave it as a gallery. Here we go. Alrighty. So thank you all for making it. It looks like only about half the students are in today, which I guess is fair because we're not quite jumping into any new material just yet. We're doing kind of an exam review. I did upload a video last night on some review of vector calculus. Mainly, I just want you to kind of have an intuition over what curl and divergence mean. Because I'm going to just do a little bit of a review of Maxwell's equations before we start diving into all of the waveguide stuff. So you'll have a break of a day or two before any real assignments kick in again, as we kind of just refresh our memories on some of that vector calculus and electromagnetic theory. Because the waveguide stuff is basically just very hardcore. Here's Maxwell's equations, here's boundary conditions, and here are the solutions that pop out of it. So I felt like it might be a good idea to really refresh some of that, because it's gonna be a little mathematically hectic, we'll say. So after that, there were some questions on the lab. Namely, I guess there was some confusion on the due date. I guess basically we agreed kind of here in class it would be due, when you come into your lab session. But in Canvas, I had to put a due date down somehow in order to post the lab assignment. And I guess I didn't think that far ahead because I can't split it between sessions. So I just slapped down some arbitrary date on like Friday. So the rule will be just, turn it in on your, when you join the lab session for the subsequent lab. And just kind of ignore the posted due date because I can't split that between the sessions and the students. Or at least there's no easy way to do it. I can try to figure something out, but for now, that's the convention. I guess for the other big questions, because I was just going to say, let's go over the exam a bit. Just kind of review where some people did well and what there seemed to be a lot of mistakes on and confusion. So feel free to just type in a question if you have something into the chat, and we'll see that. Otherwise, I'm going to just kind of casually go through the labs here, or sorry, the exam. So I'm going to start by sharing my screen. Okay, so here is the exam. Overall, the results were pretty good. I think the highest score was like 52 out of 53, and there's I think 4 or 5 of you who got in the 50s out of 53. So that's pretty good. And I think the lowest score was in like the low 70s there. So that's actually a pretty decent spread of scores there. And remember, we'll have an opportunity to retake a bad exam later. So it's not the worst thing in the world if you did terribly. So we'll just kind of go through the questions a bit. Most everybody got the first one. Just, here is a time domain signal. Here's an amplitude, there's your frequency, and then that number there is your wave number. So obviously calculating the frequency is just dividing that by 2 pi. That's the angular frequency.
That you should
know. Then the next one, for this question, a lot of people missed interestingly, because the assumption somehow got in that if it is a lossless transmission line, then the phase velocity would be the speed of light. And it would have been one thing if like 1 or 2 of you did that, but like I think 5 or 6 made that assumption. So I am genuinely curious where that idea came from. Like, did I poison your minds with this untruth? Because the rule would be you need lossless lines and there have to be no dielectrics and no magnetic materials around in order for that phase velocity to be the speed of light. So if all you are told is just here's the time domain version of the signal, then it's just there's your wave number, and you would say VP is just beta over omega. So about half of you got that, and the other half somehow got this notion that it's lossless, therefore speed of light. So if someone can show me like a clip of me saying lossless means speed of light and nothing else, I might even refund some of that that credit. But I thought I was pretty sure that you need perfect conductors and no dielectrics or anything for that to be the case. And then especially if you're just given the time domain signal here, then this information alone immediately tells you the phase velocity. So that was kind of interesting to see a lot of confusion on that. And I'm kind of curious where that notion came from. But I only took off like 1 point when I saw that. So nobody was really hit very hard. And of course, if you get the wrong phase velocity, it messes up these answers. But if you put in the right equations, nobody was docked anything on that. So most people got this correct. It was just, L was something like Z naught over VP, I believe was the equation. And most people got that right because I kind of hammered that in a lot of the practice questions. And I think C was something like 1 over Z naught times VP, if I remember correctly. And so again, most people got that fine and there was no issue there. And then the amplitude, that's kind of a gimme, right? The V was just I times Z. So you get something like 37 volts out of that. In fact, here, I'm going to pull up my MATLAB window so I'll have my actual solution key in front of me. Power. So this was an interesting one. Most people got, this was another kind of a split down the middle where about half of you got it right, half of you missed one important fact, and that is whenever you're doing sinusoidal steady state, an AC signal, the word power always means average, time average power, not peak power. So when you do something like P equals V times I, that is power in the instantaneous sense, but when you do a time average of your signals, there has to be a factor of 2 in there, like that 1/2. That's because you have the sinusoidal power going to a peak and then to a 0 again, and then you want to do the time average of that. More generally, in fact, your voltage and your current may not even be in phase. So I was definitely not a stickler for this and it didn't apply, but more broadly, it would actually have to be this equation. The real part of V times the conjugate of I, that is actually your time average power if your voltage and current are not in phase. But that I didn't want to kind of go down to that sort of nuance. But really that factor of 1/2 was something a lot of folks seem to miss. So just remember, whenever you're in the world of AC, it is just implied. It goes without saying. Power means time average power, which means it's not V times I anymore, it's 1/2. That factor of 1/2 gets into everything. This is incidentally why root mean square exists, because is a way to try and think about it without that factor of 1/2, because then you do that weird RMS averaging and you would have P equals V RMS times I RMS like that. So this is one of those nuances you just have to get used to when you're doing electrical engineering, and this distinction between voltage, current, and power. And then there's DC instantaneous power versus the time average power. So just to re-emphasize, anytime you're just in a sinusoidal steady state or AC circuit, power always will be the time average, which means you have to add that little factor of 2 there, assuming these are peaks here, like that. So I think I only docked like, I was pretty generous again. I didn't punish too much for that. Most people got this one here, if I remember, because you just have, let's see, and just a quick question. Do you care if I type out kind of the algebra here, or would you rather I sort of do it on paper? I've got the paper here we can do as well if you prefer.
I understand the typing if that's convenient for you.
Yeah. It's kind of nice just to see the question and the answer here, but if I'm going to do some algebra, I'll come over to the paper. And in fact, like for this one, you have to solve for ZL. So we actually did this in class. There was one little hiccup, I think, where I didn't actually do the derivation. I just said, someone shout the answer at me. And I don't remember if that was actually the correct answer or not. So I wonder if some people maybe missed that by misremembering. So let's go ahead and do that little derivation real quick. So I'm going to go ahead, stop sharing, go back to, so open up the other window with the camera here. What you have is your reflection coefficient, ZL minus Z naught divided by ZL plus Z naught, like this. So the idea is we're given this information and that, so you have to solve for ZL here. You just do a little multiplication times gamma equals, I apologize for being left-handed because it kind of covers what I'm doing. So I try to write and then open up and let you see here. So then we'll rearrange some terms. So you have a ZL times gamma minus 1. So I'm bringing this ZL over here. So I have a minus Z naught, and I'm going to subtract this other term here, Z naught gamma, like that. So just rearranging some terms, which I'm going to write this as negative Z naught times 1 plus gamma. So that negative sign, if you multiply both sides, you do a little bit more rearrangement here. You get the following: Z naught times 1 plus gamma divided by 1 minus gamma. So that is the formula that should have been there. So I saw a lot of answers where people were doing something like 1 minus over 1 minus. So there's some minus signs getting squished in there that messed up a lot of people. So you had sort of the right idea, just that little algebra got messed up. So I think I only docked like 2 out of 10 for that mistake, and otherwise I kind of let everything slide. I think so. Just variations on this little mistake were not too big a deal. Let's go back to the screen share. There we go. So you should have had Z naught times 1 plus gamma over 1 minus gamma, like that. So again, I think I saw a lot that did this sort of thing, and that just totally threw off your answers after that. But as long as that, this is why I really appreciate when you kind of write out your train of thought, because I can very clearly see where you go wrong. And even though there's a little bit of like a compounding, like if you mess this up, it'll mess up your subsequent answers. But that's okay. You get like 3 out of 5 for that mistake, and as long as it was kind of consistent and the rest of the thinking was okay, then it didn't really hurt you very much. So you probably saw a lot of that. So another thing I noticed, I was very clear. I put in bold letters here, parallel, but a lot of people kept putting in the series equations here anyway and trying to solve for R and C using the series. But even though we did a practice problem this on your homework, so I was kind of a little sad to see that. So we can walk through that derivation again real quick. So we come back here. So I think the correct answer, do you need to see the correct answers, by the way? I'll write that down real quick here. I'm going to open up my answer key real fast. Oops. There we go. So there we go. So the answer here was something like 3.99 something minus J13.56 ohms, like that. That's what you should have gotten.
I have a question on this problem 7 here that you have on the screen.
Uh-huh.
I have the expression for ZL exactly the way you've written it there, and also ZL equals the numeric value the complex numeric value that you've given here. But I get 3 out of 5 points, and I'm curious why.
Oh, I might have been hasty when I graded that. You can send me a note and I'll look it over again just to see if I maybe made a mistake.
All right, thank you.
Let's see. Sorry, I lost my train of thought. Oh, okay. So the question was, how do I calculate the load here? So if I just had a resistor in series with a capacitor like this, of R and C, then of course ZL would be R plus 1 over J omega C, like that. But we did not say series, we said parallel. So even boldened it to make it try and stand out a bit. So you have a resistor and then a capacitor like so. So here's my R, here's my C. So you would write this as ZL is R in parallel with 1 over j omega C, like that. So the parallel impedance equation would follow something like this. It's basically 1 over R plus 1 over this guy, j omega C, like that. So that's a little more really difficult to work with. So it really helps to define admittance. So you'd say YL is 1 over ZL, which would just be 1 over R plus j omega C, like that. So when you work with admittances, it actually makes all these fractions just kind of go away. You can still kind of crunch on this if you do the algebra. It just gets a little hectic. So this is the algebraic trick to make it a little simpler. So what you would then have is your answer at the end of the day. Here, do I have space? So you notice this is the real part here and the imaginary bit here. So you would simply say R is 1 over the real part of the admittance here. Or you could say 1 over the real part of 1 over Z. That's the answer there. So a lot of people just kind of went straight there and wrote that down, which was fine. And then of course, C would be the imaginary part of YL divided by omega. I believe that's right. So that's basically all you have to do. So the parallel just kind of makes the algebra a little bit harder, but the idea is still very much the same. So I saw a lot of folks trying to solve the series bit there when you're supposed to do parallel. And a lot of folks at least got the parallel kind of right, but they just made a few mistakes on the algebra in here. So it's just a little tricky with all the 1 over 1 overs happening. So if I at least sort of saw the right train of thought, I was pretty lenient there. But that's the basic idea. So the answer you would then get after all of this is this guy here evaluates to, you get basically just 50 ohms for the real there. And then the imaginary was about 12 picofarad. It was actually like 11.99 something, but that's what you get. Good. So it's pretty straightforward. One way to tell you're on the right track is that if you're getting nice round numbers, that can indicate you're doing it well. Because I usually will try and give you round numbers for this stuff. Let's go ahead and look at the next one here. Share screen. Here we go. Turn that off. So that was the parallel there. So I was hoping that wasn't too tricky because we did like this exact problem in one of your homework assignments. I just changed the numbers a bit. And then the quarter wave transformer. Again, this was one of the practice problems we did. So all I did was change some of the values. And there are a handful of simple mistakes. So let's go ahead and look at that real quick. So same idea. Here's a transmission line. And then we have some other line here. So this is a Z0 here. There's going to be some other impedance here called Z1. And then we just have some load like this. So RL. So I think I said 50 ohms here. What was the value? Oops, excuse me. And then this guy here was 125 ohms over there. And so to design a quarter wave transformer, you only need two pieces of information. You need to know what is the length here, and then what is the impedance of my transformer in here. So this the first part of that is super easy. Just Z1 was the square root of RL times Z0. You get something around, what do you get? About 79 ohms if you do that. So that's a super simple gimme question there. I think most people got that. And then the length was the tricky bit here because you need to know the wavelength in here, which was a function of the phase velocity. So we said phase velocity is 0.66 c. And I swear, I think a few people maybe missed this step and just set it as C, so that messed up your length a bit. So I think I was fairly lenient if I saw that, just again, 1 or 2 points off for that kind of thing. Because it gives you a pretty straightforward answer. Because remember, C is frequency times wavelength. So that means your wavelength is going to be your phase velocity over the frequency. And that evaluates to something, but we don't care about that because I just put it in MATLAB. Because my L is going to be then lambda over 4. So that you get, I think this was around 80-ish centimeters. And then when you divide by 4, the exact answer was 20.61. Oh, millimeters, excuse me, millimeters, not centimeters. So you get around 80 millimeters for the wavelength, and then your L becomes about 20-ish. So those were the correct answers there. And again, I think the only mistake I saw was people forgot to account for the phase velocity. Because I said it right there in the question, it was 2/3 the speed of light. And I think I even messed this up a lot when I was doing the answer key, because if you forget to assign this variable here, it carries over from your previous problem if you don't clear your variables. So I remember running into a lot of trouble. That's why I specifically said when you're doing your exam, if you're writing a MATLAB script for this, always clear your variables between one answer set and the next, because if you don't if you forget to overwrite the wrong variable, it will carry over bad information from the previous problem. So I think there's a few that just missed up the length here, but otherwise it was pretty straightforward. And then the final question was to calculate the return loss. So remember, return loss is 20 times log 10 of the magnitude of your gamma. So again, we did this in class. You did this essentially for your lab, where you're creating a plot of this. But a lot of folks didn't seem to get this definition, because I guess I didn't quite browbeat it enough. It wasn't explicitly said return loss in the lab. I just said you calculate this thing. But we did do this practice problem in class, so I felt like that was a pretty good premonition for what this thing should be. But basically, we just gave you 2 frequencies. So you had like 2.2 gigahertz. And then there was an F2 was 2.6 gigahertz. Whereas the center frequency, F0, was 2.4 gigahertz, like that. So this was a good practice on using the transmission line impedance equation. So you remember Zin was going to be, and I think this is exactly one of those mistakes I made during the practice, which I tried to make a big fuss about. But when you calculate it, you have to use the impedance of your quarter wave transformer here, not the transmission line here. So in your mind, you have to kind of imagine this is a box here. And what is the equivalent input impedance looking into here, my quarter wave transformer? So the characteristic impedance is Z1. And then if I can remember my transmission line impedance equation, let me open that real quick. Yeah, so then you'll get ZL plus JZ0 times your tangent of beta L. Oh, sorry, and again, see how you want to write Z0 here. That has to be a Z1. Like my brain just could not remember to put that there. And then you get a Z1 plus JZL times tangent of beta L. So the beta changes with frequency, but this is the mistake I saw a lot, is you have to put the Z1 here, not the Z0. So, and then that gives you 2 values for your Zin, which then of course, your gamma would simply be Zin minus Z0, or Zin plus Z0. So you calculate your gamma at each of those frequencies. And because they're symmetric, you actually get basically the same result. And I remember one student didn't get the right answer, but they were smart enough to say that it's supposed to be symmetric, right? They didn't have time to finish, but they said, I should at least expect them to be symmetric here. And I was like, that's good. That shows you kind of are thinking ahead there. So I'm generally pretty generous as far as credit and partial credit goes when you explain that kind of thing. You plug that into here. Yeah, this equation. And the answers you get for your R, your return loss, was about, let's look at the answers here. Yeah, you get about minus 24 dB. And that's you get it for both frequencies because they're symmetric. They're technically not identical, but they're accurate out to like 3 or 4 decimal places. So it's like, who cares? And I genuinely don't care about that minus sign. Like it technically should be negative whenever you plot, your reflection coefficient. But then return loss is actually supposed to be defined by this negative sign. And it's just a giant confusion that I don't want to be a stickler over. So I didn't care if you had a plus or a minus here at the end of the day. But that 24 decibel was the important answer. So again, I think it was about half kind of got it perfect. The other half made this sort of mistake here. Forgot to use the ZN equation and did some other variations like that. But that was the basic thinking. Were there any, I guess, questions there? That's the whole exam. So I felt all right in terms of just the grade spread. So let's stop sharing here. Oh, sorry. So I felt pretty good about that. And we'll try and do a little bit better in terms of being more clear in the future. Like I probably could have written time average power instead of power. The idea of return loss, I don't think I ever said return loss on a homework problem per se. I just had you calculate the thing. So little bits of miscommunication may have snuck in there as well. So I'm kind of going to try and be more mindful of that. But that's all you really need to know, in my opinion, for the transmission line theory, is just this idea of characteristic impedance. How do I go from time domain to phasor domain? This equation in particular. And we didn't really do too much Smith chart stuff, mostly because I just did not want to have you spending forever trying to fine tune a plot. So that's why I had you do a lot of homework problems on that, just to kind of get that experience, but I did not want to, it just felt like it would be a lot of work to try and have you do some sort of Smith chart plot on an exam under all that pressure. So especially you did it on your lab, you did multiple practice problems of it. So I kind of weighed that and decided to focus a little more on this other stuff instead. And that, oh yeah, so there was a couple little incidents. I was thinking, how would you feel if I allowed a 2-minute break? Just in case you have to get up and go pee or something. I think that's actually an option we can allow. There's some complaints there. There was 1 or 2 students who were reading problems out loud. So that tends to trigger a flag because you're not supposed to be talking, right? If you're in a classroom with nobody else around, you should be quiet. But if you're there alone in the room, it's not a big deal. But just kind of be mindful. Those little things you do can trigger the proctor flags or the little incident reports. But other than that, I think that was it. So I felt like it was pretty good. Most people had a good experience. I'm kind of curious for feedback on just how the ProctorU experience was. You can either just put it in the chat or email me about it later, or if you feel like it was pretty good and we can do this more in the future, then I guess this is how we'll do it. And I know it's not ideal because just the online format is a little frustrating, but it just kind of is what it is. So I just want to also thank you all for your patience and giving me your feedback in terms of what's working and what's not. And I'm trying very hard to really improve this experience as we go, because it is definitely new for a lot of people. So I definitely appreciate your patience and your sincere feedback to help things improve. So if there's any other comments on that, again, you can contact me via email. You can just type something in the chat and we'll address that. Oh, there was one little thing. This is a total nitpick. I was looking at some of the labs for lab 1. Or sorry, lab 1, where people were doing their plots of gamma. So as a general rule, when you do your return loss, so it's your magnitude of gamma in decibels here, and then you have your frequency response. And what you generally are expected to see is something kind of like this. And that's if you truncate it with your axes there. Because usually this is kind of the information we care. But if you were to zoom way, way out, this thing wants to go down to minus infinity, right? So this is a purely aesthetic nitpick. So it's not wrong when some people turn this sort of thing in, but it just looks horrible if you're going to do this on a scientific publication. But if you just let MATLAB scale the axes automatically, what you end up seeing something that kind of looks like the following. So here is like 0 dB, and then here is like minus 300, and you see your plot do this sort of thing. Does that kind of sort of make sense? So all the interesting stuff is happening up here, but because your axes are scaled poorly, it kind of looks awful when you do that sort of. So I was just left a little bit of feedback saying it's not wrong, but as an aesthetic thing, whenever you plot kind of one of these bandwidth frequency response sort of things on a decibel scale, you don't want to let it shoot down to negative infinity here. Usually you want to chop it off at like minus 80 dB or so, and then make that your bottom slice of your window. And it makes your graph a much more easy and legible when you do that sort of thing. So like I said, that's purely an aesthetic nitpick. It's not wrong with a lot of the plots, but I just saw so many students doing it in their turn and stuff, I had to say something. I am a stickler for that sort of thing, so I like to make a fuss about it. But I won't necessarily mark it wrong unless it just happens over and over and over again, or it's egregious. Okay, so that I think was my only little issue with the labs. So at this point, we can talk a little bit about the upcoming lectures next week, because we are going to shift gears and start doing waveguides. So over this weekend, I got my work cut out where I have to now start posting a bunch of material on that. So let's just look at the book real quick. So we're getting into chapter 3 here. There we go. Waveguide theory. So this is going to be some very hardcore electromagnetic field solving. So if you're not comfortable with your vector calculus or with your Maxwell's equations, now is your chance to really get a little more brushed up on that. And I decided, because yeah, not everybody's really on the same level, so I'm going to do a little bit of kind of review on just basic background, like what does divergence and curl mean? So I've uploaded some little videos on that. I'm going to do a little bit of a review of Maxwell's equations, like what are Maxwell's equations really telling you? Because again, I don't think that stuff gets emphasized as well as it could be when you take a class like 3300, or if you do like your physics 2. You're exposed to it, but there's certain just key ideas from a mathematical perspective that you kind of need to be very comfortable with. So a simple question like, here is the curl of V. What does curl even mean on a vector field, right? I remember taking vector calculus and thinking, I can work with this mathematically, but what does it really represent, right? And then you have ideas like divergence as well. Because you notice in this section, it's just going to be, here's Maxwell's equations. Now we're going to start solving a bunch of stuff, and it's going to get a little hectic in terms of the partial differential equations, the vector calculus, and some of the fun solutions after that. So just kind of relax for the next day or two as we do some review on just the mathematical formalism there. So I'm just going to upload a video or two on that stuff. And by next week, mid to next week is when we'll start doing our actual waveguide solutions here. So in particular, the parallel plate waveguide is one of the coolest things ever, because the math is just within reach to grasp for most people. And it has a whole lot of interesting concepts that come out with the mathematics of this stuff. And then eventually you get to the rectangular waveguide, which we'll kind of touch on a little more. Here we go, there's a picture. So what happens if I excite an electromagnetic wave inside of this enclosed space here? Let's see, and then after that, there's the circular waveguide. Where is that? There you go. So it's interesting in the sense that it's very slowly building in complexity, right? So first you'll do the parallel plate waveguide because it's a nice simple mathematical model. Even if it's not a realistic thing, the mathematical methods you see in it are extremely helpful to build on the more complex stuff. So the circular waveguide is kind of interesting. And in particular, if you get into any sort of just antenna and radar kind of applications, this whole waveguide notion is going to be very, very important. So yeah, all the same, and you notice it's a lot of the same ideas, same math, it's just going to be like in cylindrical coordinates instead of rectangular. So I like how it very carefully builds on itself there. And then of course, we're going to solve the coaxial cable to death. so that's an interesting fact is we've so far kind of been assuming something like a transmission line just has a voltage and a current in it. But if you go very, very high in frequency, eventually the waves can start bouncing around in that space inside of those two conductors there. And you can actually solve that stuff exactly and see what happens if you overdo it. I guess I'm a little disappointed that they don't do the dielectric waveguide, but that's more of an optics thing than I guess a microwave engineering thing. But the mathematical methods here you do for all these waveguides is very helpful if you want to go into something like optics. And in particular, if you ever do anything fiber optics related, this waveguide stuff is extremely important. And I guess Steve Blair, I took a class from him, I think it's called Integrated Photonics, where you just kind of do nothing but waveguide stuff in kind of higher level descriptions of these things. So this is a good primer for a lot of advanced classes. And then of course there's the microstrip line, which is what we'll actually be using in our labs later. So it's helpful to get a nice firm appreciation of what in the world is happening with the electric and magnetic fields inside of this geometry. And it's interesting, like there are no closed form solutions for this. We're just going to kind of wave our hands and get some kind of best guess solution to this stuff. But that's going to be one of your labs actually is what can we do with some of the approximations there. All right, and then that's pretty much most of the stuff we care about waveguides. There's some other stuff here we're not really going to touch at the end, but that's waveguides in a nutshell. So you're going to have the parallel plate, the rectangular, and then there is the circular, and then the coaxial, and then microstrip at the end. It's going to be a pretty nasty mathematically, so I'm going to try very hard to just sort of baby step through it and do a lot of very careful derivations. And I strongly recommend as you do some of the math on this to take your pencil, like literally put it in your hand and follow the derivations yourself. See if you can kind of make sense out of it. Because this, when it's this mathematically heavy, then there's going to be a few questions here and there that are going to be, you know, starting here to prove A to B to C kind of stuff instead of just plugging in equations. So be prepared for, I guess, kind of a step up in the mathematical intensity. But then for what it's worth, after that, it's not going to quite be so bad. When we do like network theory, you're not going to be solving PDEs anymore. So I would probably describe this next 3 weeks as going to be kind of, I don't want to say like the hump, the crux of the class in that sense. So just be prepared for lots and lots of math. And I'll try to, and again, feedback is going to be helpful because I particularly find this waveguide mathematical stuff awesome. And I'm going to have to rein in that enthusiasm to be mindful of your guys' level here. You've just barely been exposed to it, and I've been doing this stuff for 15 years. So if I get overly enthusiastic in some of my homework projects and things, be sure to ask basic questions. Because again, simple things like what is curl or divergence, you know, you may have seen that in your vector calc class, but it may not be super intuitive, right? And just simple mathematical methods like separation of variables for solving PDEs is going to be a little squishy, right? Maybe some of you are kind of happy with that and comfortable. Some of you are not going to be. So definitely please give me some feedback on how you're feeling as we go through this next session, because this is definitely going to be kind of a disparity between those who are mathematically comfortable and those who are just kind of scraping by on the skin of your teeth, I guess. So that's kind of all I had today. So I encourage you to just watch that first video, and probably I'll have more stuff out by Sunday, and we probably won't have a new assignment until a little after Monday, after I've gone through all the material and been able to work through the material enough to start figuring out some good homework problems. So enjoy the break while it lasts, because next week it's going to kick up into high gear. So I will open the floor to any questions or concerns if you want to talk about that. Otherwise, that's all I've got for you today.
You mentioned that you uploaded a review about the vector calculus discussing curl and divergence.
Uh-huh.
Are you also going to upload a second video that was going to discuss I think you mentioned Maxwell's equations. You wanted us to have an
Oh,
intuitive.
yes. Yeah, I put together a little PowerPoint slideshow. I just haven't recorded it yet. So that one I need to do by the end of the day because it was sort of supposed to be for today's lecture. I just didn't quite get around to that second video yet.
No problem. All right. That was my question.
Because yeah, like if you think about it in terms of just the mathematics. So here's Faraday's law. The curl of E is the negative time derivative of the B field. And then you have Gauss's law, this del dot E is equal to rho over epsilon naught. And then there's the other two laws. So you have to be comfortable with this curl and the divergence together with Maxwell's equations. So then of course, curl of H was equal to a bunch of stuff. And then you have a del dot B equaling stuff over here. So very important that you just kind of have an intuitive sense of what a curl and divergence. Because there's a thing called the Helmholtz theorem. And I really wish vector calculus classes talked more about this because this is central to electromagnetic field theory. And basically, it just says, imagine some vector field. I'm just going to call it F. And it can be a function of X, Y, and Z. So at every point in space, there is a vector. And you'll also see a notation that might look like this, F of R. So R would be a position vector representing these three coordinates. And I don't know what that field is. I do, however, know three pieces of information. One, I know the curl of F. Oops, sorry, that's a little sloppy. And I know the divergence of F. So I'm going to put a little check saying this information I have and this information I have. And then the third piece of information is I know the normal component of F, so n dot F, across some boundary S, some surface. If you have these three bits of information, then F is unique. And that sounds a lot more boring than it is. It actually says, given these three pieces of information, there exists a unique solution for this vector field. One and only one solution for F will satisfy these three things. So it sounds a little weird, but then you look at Maxwell's equations. I have these two vector fields, E and H, or E and B, depending on the constitutive relations. So here is Faraday's law telling me the curl of E, and then here is Gauss's law telling me the divergence of B. So that satisfies those two conditions here. And the third is up to you, depending on what specific geometry you want to model. Like, right? Like it could be a microstrip, could be a circular waveguide, could be a rectangular plate waveguide. It could just be a little current source floating out in space with no boundaries anywhere out to infinity. But this thing is up to you to impose on the geometry that you're interested in. So Maxwell's equations are essentially telling you these two bits of information for the electric field and the magnetic field. And then the geometry you're interested in determines the third bit. So it sounds a little dry and technical from a mathematical perspective, like, oh, it's unique, so what? But you're guaranteed that a solution would exist for that particular geometry given Maxwell's equations. So that's kind of the idea. So actually calculating the solution is generally very hard, and there's kind of an art to it, I guess, when you get a lot of practice. But just knowing that it exists and it's unique and it's out there is kind of what Maxwell's equations are saying. So I have a curl, I have a divergence, and I have boundary conditions. There exists a solution. We're not going to tell you how to find it. That's up to you to be extremely clever, but you know that it exists, and that's the information you need to guarantee that unique solution. Okay, so I'm going to do a little separate video where I kind of emphasize this stuff again in a little better detail. But that's the idea of why I'm really emphasizing, you need to know what curl and divergence kind of mean. But it's the idea of here's the twistiness of a vector field, and here is sort of the radially outwardness, straightness of a vector field, and then boundaries on it. That kind of makes sense. So again, I'll do kind of a recorded PowerPoint presentation of this with much cleaner notation than my handwriting. But that's the idea at the end of the day. All All right, was there any other questions or comments? We still got another few minutes. Because if you got nothing else, then you're free to ask a question or just head on and enjoy your weekend while I put up some more material for you. Oh, one quick. Did engineering calculus series cover? What is the engineering calculus series? What do you mean? Is that like a series of videos? What is that?
When I did my undergrad at the U, they just started the concept of engineering calculus series, because before you took Calc 1, 2, and 3 from the math department.
Right.
And then you took your PDEs and your ODEs and linear algebra. And apparently the engineering department was complaining about too much math. So they
can't have too much. Yeah.
So they condensed the math classes, reducing it by 2 overall classes. And so instead of taking Calc 1, 2, and 3, where 3 is an entire semester focused solely on vector calculus, they got rid of it. And then they took key parts of vector calculus and shoved it in with partial differential equations, I think.
Ooh.
I was just asking if some of the other students have taken it, and if the actual, because I think, because I took math from the math department, Calc 3, I was a lot more comfortable with this stuff because I had a better math foundation. I just got the other students if it did cover this stuff.
No, that's a great question, because I did the Calc 1, 2, 3 thing. So when I made that last video, I kind of assumed you've already dealt with curl and divergence, but you just dealt with the mathematics of it, not the intuition. So I kind of assumed you were sort of already comfortable with that. And if you're not, then some of the stuff at the end might completely blow your mind and be not make any sense. So that's actually a good question. Is everyone have at least some basic treatment in vector calculus? Because this will kind of influence how I go about the rest of the week here, and some of the hand holding and the problem assignments. So now's your chance to say, nobody understands anything, please take baby steps, or yes, we're comfortable, please open the fire hose.
I took the Calc 1, 2, 3 path as well, so I can't speak to engineering calculus thing, whatever that is.
In fact, yeah, everyone should have had some at least preliminary exposure with PDEs, right? You know, solving the Poisson equation and maybe the wave equation, I hope. Because we're going to be doing a lot of just wave equation stuff, or specifically the Helmholtz equation, because we're doing sinusoidal steady state. So think of that as the wave equation, but with phasors. So I hope you're all kind of comfortable. I'm going to do my best to be very kind of baby steppy through some of the difficult bits. And so it sounds like nobody's saying anything. So you're either all getting a sandwich or you're all totally comfortable with that. So that works for me. So I hope I hope you love math as much as I do, because we're going to do some vector calculus. All right, then I guess on that note, I'll just stop recording.